Right, so we're all familiar with Murphy's Law. Anything that can go wrong will, and at the worst possible time. Well, this is a testament to that. Not 10 minutes ago, I tested this, and it was working fine, so I'll have to advance slides the old-fashioned way. So, really great to be back at the BayesiaLab Users Conference again. I missed the last three. As I mentioned to Stefan, now that I'm self-employed, I have a decision maker who's more enlightened about things like whether it's a good idea to spend money to go to the BayesiaLab Users Conference. So I'm back again after a 3-year absence. In my practice, I do a lot of work that's about helping clients figure out how they can influence the market in their favor. A lot of times this is as simple as, how do we get people to buy our stuff instead of our competitors' stuff? Problem with that is that you can't influence that outcome directly. You can't just ask them nicely, please buy our stuff instead of our competitors' stuff. You could try it, but it's not likely to be very effective. So you have to figure out, amongst the things we can do related to product design and product marketing, what would represent the most effective levers. So it's a lot about predictive modeling. All right? What brand attributes should we emphasize? What product reasons to believe should we emphasize, et cetera. And in predictive modeling, of course, how accurately you can predict the outcome that you're trying to learn how to influence is a very important consideration. I've used BayesiaLab to very, very good effect toward that objective, and coming up with predictive models that are very good at accurately predicting the outcome that we're trying to move, be that brand choice, purchase likelihood, what have you. But I got interested in neural nets because I know that under certain circumstances they can be as accurate or even more accurate. And so that's what led me to this investigation on which I'm going to report some very initial results to begin with. Now, come on, move this, please, huh? Let me try something here. Okay, it would appear that my computer is basically frozen. You have to hold your mouth just right for this to work. Before I continue, though, I did want to emphasize that the findings I'm going to be presenting here are based on one very preliminary experiment. It'd be intriguing if these findings accrue to other data sets, but that may or may not be the case. This data that I've used here is very well behaved. It's very ordered, and I'll explain what I mean by that. And so the same results might not accrue. You might get different results if you try this at home. But still, I think you'll find that the information is interesting, and it does present some potentially intriguing possibilities. So, quick overview of what is a neural network for those of you who may not be particularly familiar with it. It's a technique of predictive modeling that's loosely patterned after the brain. It's constructed of one or more hidden layers. So in the center here, this is the hidden layer. The inputs are your baseline variables. In this case, it will be attributes. And a backward propagation technique is used to derive weights that will connect each of the inputs. The weights are represented here. Each of the inputs connected through the weights to the hidden layer. The hidden layer is then connected through further weights to the output layer, and the output layer provides the prediction as to the output class. Okay? Under certain circumstances, especially with rather nonlinear data, this can be a very effective method of predictive modeling. Now, in my business, as I said, I try to help clients figure out how to influence market outcomes in their favor. That means you have to understand the why behind the prediction. One drawback with neural networks is that they tend to be very black box. This is not, as neural networks go, this is not particularly complicated. It's got one hidden layer, and it's just for recognizing handwritten digits. But you can see with all the weights that get involved in here, there are thousands of them. So there are thousands of potentially causal paths, thousands of aspects to explaining the why behind the predictions that are coming out. So if you're in a situation where you need to be able to explain why the neural network is making the prediction it is, it can be very difficult to impossible in order to do that. So it's a big issue right now. How do you go about achieving explainable neural networks? Well, we take a step back and we ask, what is a neural network node? Because in a sense, explaining a neural network outcome is about explaining the nature of the node. So I think it's accurate to think of a neural network node as a kind of latent variable. That being the case, It may be similar to a factor in that it aggregates information from multiple of our observed variables. It's latent in the sense that it's not measured or observed directly, and it can be indirectly measured based on mathematical derivation from those observed measures. However, unlike a typical factor, a neural network node is not just derived out of the observed variables. It is also derived, or emerges, if you will, from a derived predictive power against the outcome class, okay? And that's the important distinction. To put it a little more pictorially, if we're looking at a factor, you have the factor as a latent construct, and it is derived out of these measures, 2 or more measures, and then you look at how the different measures weight against the factor, and you interpret what that factor may be about, right? And it can be, again, indirectly measured through calculations. Think factor scores in principal components analysis, for example. A neural network is like a factor, but again, it's a little different. It is derived in part out of the nature of these observed measures. These are the inputs in the neural network. But it also is influenced by the outcome predictive power. That is, it is a latent variable that is created in a way so as to maximize its predictive power against the outcome class. And this makes it very potentially useful in applications such as I do, where you're trying to maximize the accuracy with which you can predict that outcome variable so as to maximize the confidence that my clients can have in strategies that derive out of that predictive model. So this is an important difference, the fact that it's outcome predictive power that is also influencing the nature of the neural network node. So for this test, I used the SONAR data set. Some of you may be familiar with it. It's publicly available. And it was created by bouncing SONAR signals off of a sample of metal cylinders and off of a sample of SONAR signals bounced off of a metal cylinder versus bounced off of a roughly cylindrical rock. And it yields 60 numbers that all range from 0 to 1, and each number represents the energy within a particular frequency band. It's integrated over time. So it's physical data. It's not like the survey data, market research survey data that I so typically deal with. But again, it's the ordered nature of this data that makes it very amenable to this particular experiment. And you'll see more what I mean by that. So in this experiment, I use the SONAR data because it organizes into very, very linear, sort of well-ordered contiguous factors. I produced supervised models for predicting the rock versus mine outcome using a neural network and then also using a Bayesian network in BayesiaLab. Started out with that as the point of comparison. And then I contrasted the factors that are produced by BayesiaLab's variable clustering to the neural network nodes that emerge from the neural network analysis, and contrasted them in terms of their characteristics as latent variables and in terms of their ability to accurately predict the rock versus mine outcome. Now, in BayesiaLab, I ran a factor analysis using variable clustering and multiple clustering. It yielded a 10-factor default solution, which looked good. And then I used 2 types of BayesiaLab models in the analysis. One is a simple naive Bayes, the factors predicting the rock versus mine outcome. And then for another part of the comparison, I used a PSEM model for testing the predictive mutual information of the 60 baseline attributes as they operated through the 10 factors. Okay. Okay. For the neural network models, I used the RapidMiner neural network operator to run a simple one hidden layer neural network using 10 neural nodes. I chose 10 to parallel the 10 factors that the BayesiaLab default solution had derived. While the BayesiaLab network predicts the outcome with about 75% accuracy, this neural network achieved about 85% accuracy. All right, that's good. That would be significant to clients of mine. But again, just looking at the neural network, we don't know why. And more importantly, I can't say, oh, the neural network is telling us that if you emphasize this, 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 and this attribute, that would be your best strategy for maximizing the outcome. So it's very useful to understand the why behind this. So I imported the 10 neural network nodes into BayesiaLab to use them as predictive variables, latent predictive variables. And in a simple naive Bayes model for testing just the neural network's ability to correctly predict the outcome of class in one case, and then I also used an EQ model for a different kind of comparison to the BayesiaLab PSEM, which I'll show you later in the presentation. This just gives you a quick visual illustration of how well behaved this particular data is. This is a maximum spanning tree network on the 60 attributes. If you run an EQ network, which allows for more than just the nearest neighbor connections, you get the same network. So it's very, very well behaved because it's basically across frequency bandwidths. So it's physically continuous. Again, that makes it very suitable for this experiment because we can expect how it's going to behave in a very orderly way. So this is where it starts to get interesting. Here we're comparing the 10 factors against the 10 network nodes, just in terms of their mutual associations with each other. And we can see, first of all, with the factors along the bottom row and the hidden nodes here, there is no one-to-one correspondence between the factors that were produced and the neural network nodes. Right? There are some associations, but definitely no one-to-one correspondence. And we see that the node force in the factors is concentrated primarily into 3 of the 10 factors, whereas node force in the neural network nodes spreads out much more evenly. It starts to give us a little hint about the differences of what's going on here. And we also find that the BayesiaLab factors in which the node force is most concentrated, factors 3, 0, and 6, they associate most with certain subsets of the neural network nodes, but definitely they spread out. Again, there is no tendency for one of these higher node force factors to associate particularly with certain nodes. So the neural network nodes are definitely gauging something different in their nature as latent variables. So in the predictive contest here, we use a naive Bayesian network with our 10 factors as predictors, and that achieves about a 75% accuracy in trying to predict the outcome class. I use a naive Bayesian network in BayesiaLab to predict the outcome class using the 10 neural network nodes as predictors, and we get a 98.6% accuracy. Kind of blew me away a little bit, because remember, when we do the neural network per se, we get about 85% accuracy. But if we take the nodes created by that neural network and we bring them into BayesiaLab and use them as predictors, we get this 98.6% cross-validated accuracy. Now, I want to emphasize, I don't expect that this would accrue with a lot of other types of data. Again, this is a very certain kind of data based on a physical phenomenon, very well ordered. But it did really pique my curiosity, so I repeated this experiment with survey data. We used for a social media platform to predict how brand perception attributes predict the heaviness of usage of their platform and other platforms. And the initial BayesiaLab model that I had used in that project only maximized at about 67% accuracy. That was as accurate as I could force it to get. When I used this approach, I got an accuracy of about 85%. So an increase of about a third in the predictive accuracy of it. So that's some very initial evidence that this might be a usable trick in other types of data applications. But it gets you thinking, what is it? What are these things? Right? What is it about these neural network nodes that gives them such high predictive power? We know conceptually it's because their derivation is based somewhat on creating latent variables that can accurately predict the outcome class, but that are also derived from the observed variables. But I wanted to understand at a more specific level what's going on here. So one thing I found out is that when you use the 60 attributes to predict the neural network nodes and the factors, I find that the neural network nodes individually, the other way around, that if you use the neural network nodes one at a time to predict the outcome class, and you do the same with the factors, we do find, as you'd expect, that the neural network nodes are significantly more accurate in predicting the outcome class, running from about 57 to about 82% cross-validated accuracy versus the factors going from about 45% to about 76%. We'd expect that. If we look at the naive Bayesian model predicting the outcome using the 10 BayesiaLab factors, again, it achieves about 75% predictive accuracy against a 50-50 outcome. So that's not bad. Most of the predictive power is derived from 3 specific factors, and the other 7 factors don't really come into play very strongly. And when we use influence on target node in BayesiaLab to try to understand the pattern of specific predictive influence that the factors have on the neural network nodes, we can see that, and these are ordered from the most to the least predictive, we can see that there's a fair amount of variability in the influence on target patterns that the factors achieve. These first 3 start out looking fairly similar, but then it starts to change, and then we get down to the least predictive factors, and there's really no difference in the factor states patterns for the rock versus mine outcome. We do the same exercise with the neural network nodes, taking the 10 nodes and using a naive Bayesian network to predict the class outcome. We get this much higher predictive accuracy, 98.6% cross-validated, and we see that the mutual information with the outcome class is spread out a lot more across the nodes. And they do, as a matter of fact, the sum total of the relative information that we get is about 4.5 times as high as that we get in using just the BayesiaLab factors. And this is interesting. The 10 nodes all show remarkably similar patterns of influence on the target. Let that soak in for a second. I mean, they all show this same basic pattern of the rock class being low on the first 2 states and high on the third, and the opposite amongst the mine class cases. But they're not predictively redundant. And I'll drill into that a little more. And just to figure out, is this a BayesiaLab thing particularly? The BayesiaLab is able to take these nodes and achieve such high predictive accuracy, and it turns out it's not actually. If I use these nodes as predictors using 8 other predictive modeling techniques and find that it looks like any method that is good at handling nonlinear relationships between the predictors and the outcome class can take these neural network nodes and achieve a very high cross-validated accuracy in predicting the outcome class. Also found it interesting that the highest accuracy is achieved by BayesiaLab's naive Bayes algorithm, whereas the RapidMiner naive Bayes achieves amongst the lowest. So I discussed this briefly with Lionel, and he agreed that, naive Bayes is naive Bayes, so probably I should get in touch with RapidMiner and tell them they need to check out the programming on this. So what about the explainable part? Okay. It looks like there's some evidence here from this experiment that neural network nodes as predictors in a BayesiaLab model might be able to significantly increase your cross-validated predictive accuracy. But it's also the case that BayesiaLab provides a promising means of understanding the operation of these neural network nodes and getting at the why behind the outcome, to figure out how are they translating these 60 attribute inputs into this accurate prediction of the outcome class. And again, in the applications that I most often work with, my clients want to know what are the levers we need to pull. Out of all the things we could prioritize, which ones? So the predictive accuracy in and of itself is great, it's important, but it's not enough. Well, so this kind of gets down to understanding how the attributes predict the nodes so that we can understand what's happening with a given node as it in turn predicts the outcome class. We do find that, as you'd expect, the attributes predict factors more accurately than they predict the neural network nodes. That makes sense. The factors derive entirely from the observed variable, so you would expect to see this. But when you look at the patterns of correlation between the 60 attributes as they predict each one of the factors or each one of the nodes, some interesting aspects come to the surface. This is just using, looking at Pearson correlations, using BayesiaLab's mapping function to look at Pearson correlations as as the 60 attributes collectively predict the factor outcomes. And these are ordered in terms of the factors 1, 2, 0, 1, 2, 3, etc. up through 9. And the factor numbers here as they correspond to those. So you can see the positive correlations with the factors. They run in this stair-step fashion as indicated by the green arrows, as you would expect them to do. against the factors. This is exactly what you would expect to see. And they will tend to have negative correlations with other parts of the frequency bandwidth. Right? Again, very well ordered, very well behaved data. This is what you would expect to see. If we do the same exercise with our 10 neural network nodes, kind of an interesting outcome here. Two main things pop out. One is that obviously there are four types of nodes, four distinct types of nodes that are in evidence here. Right? These first two, nodes 5 and 3, are somewhat unique. But then you have 2, 6, 4, and 1 all showing the same basic pattern of correlations with the input attributes. And nodes 9, 7, 8, and 10 all showing another basic pattern. There's some subtle differences, but the similarity between the tetrads here, if you will, is very readily apparent. Okay. And this is just another way of looking at that same thing. These are just absolute values of correlation with higher values shaded to green. And you see how the two main things that come out here is that the network nodes, neural network nodes, will tend to span two or more contiguous factors in terms of their higher correlations. And also that you see these four distinct patterns. Okay. So as we showed, the Pearson correlations between the baseline attributes and our 10 neural network nodes show that the 10 nodes group into these four general types of attributes to nodes correlation patterns. And this suggested to me that, well, maybe a neural network that represented only four latent constructs would serve to get equally accurate prediction. And indeed, when I ran a neural network with just four layers in the hidden variable, it actually achieved a slightly higher predictive accuracy, getting close to perfect with 99.5% accuracy. And this all suggests that, okay, well, maybe this is also a good way to get an initial handle on how many nodes do you need in a neural network. Because when you run a neural network, one of the first questions you have to answer is, how many nodes should there be? How many hidden layers and how many nodes in each hidden layer? And this suggested that, well, four might make sense here. Indeed, when I do that, what I see is that three of the four patterns are represented pretty true to the way they were before. The larger graphs here are from the new 4 neural network node neural network model. And you can see that 3 of them correspond very closely to 3 of the patterns that were observed amongst the 10 neural network model. This fourth one that emerges does not correspond in terms of its Pearson correlations patterns. It does not correspond to any one of the 4 patterns that we saw in the 10 node model. But interestingly, it replaced the node that had the lowest singular predictive power against the outcome class, and it replaced it with a node that has the highest singular predictive power against the outcome class. And maybe this is where that little bit of additional predictive accuracy comes from. Okay? And again, this augurs back to what I showed you before. These 4 nodes, when you look at the influence analysis on target node, they have virtually, not identical, but obviously very much the same pattern of influence against the target node. They all have this low on the first state, high on the other 2 states for the rock cases, and the opposite for the mine cases. And when you run these just one node at a time, predicting the outcome class, you get these different levels of predictive accuracy, none of which are all that close to the 99.5% accuracy that you get with all 4 of them together, which suggests to me that even though they show very similar patterns of influence on target, they're not predictively redundant. There are some subtle differences here that are coming into play in terms of creating this holistic ability to predict the outcome class with such high accuracy. So let's go in deeper on the explainable part here. Again, this experiment suggests that you can get good increases in predictive accuracy. And we've seen that whether you're using 4 or 10 neural network nodes, you get similar patterns in terms of the nodes' correlations with the input attributes. But you still need to know, how do these attributes differ from each other how do the nodes differ from each other in terms of the attribute influences, because that's where the Y part can be derived. Well, BayesiaLab offers an effective means of explaining the neural network nodes by revealing which specific observed attributes most strongly drive each of the neural network nodes. And for this exercise, I'm going to go to the 4-node model because it's just simpler in terms of the graphics and what you have to look at. So the logic here is just, okay, we've got these 4 neural network nodes. We can use things like influence on target, the various tools that BayesiaLab makes available to understand how each node is being driven by different patterns of the 60 attributes. And then that translates through to how these 4 nodes are operating varyingly to predict the rock versus mine outcome. So there's a logic of interpretation or a flow of interpretation that we can do here to get an understanding of how the rock versus mine outcome is being achieved in terms of differing amounts of influence from the original 60 attributes as they operate through the neural network nodes. This is very similar to how you would use BayesiaLab in a PSEM mode. Right? So the key points that I'm about to show are, one, there are nuanced differences in the combinations of influence that the different attribute ranges have in imbuing the neural network nodes with this holistic capability to so accurately predict the outcome class. Each node will tend to show the highest degrees of mutual information with specific attribute ranges, that is higher than the other 3 nodes, but it will also spread additional mutual information across other attributes in other ranges, and that's where that nuanced, more subtle distribution of attribute influence comes from as compared to straightforward factors. So the logic here is that by carefully interpreting which attributes are most strongly predicting each of the neural network nodes, you should be able to understand how the network is predicting the outcome class, right? And again, this logic, basically. Okay. So what I've done here is just run relative mutual information scores of each of the 60 attributes. These are represented across the bottom here in the colors representing the different BayesiaLab factors, from attribute 1 to attribute 60. And then the bars just show the relative mutual information score of each attribute as it predicts the node outcome, not the outcome class, but the node, the nature of the node state. And we can see, for example, here that node 1, which by itself predicts the outcome class with almost 80% accuracy, it has dominant, what I'll call relative mutual information, RMI dominance, on 4 selected attributes, but then also 2 attributes here, 4 attributes here, so 10 specific attributes. But it's also, as you can see, the other blue bars here, it's also spreading mutual information association across a number of other attributes as well, subtly differing combinations. The other nodes do similar things. Node 2 is more concentrated into certain bandwidth areas, in this more central part of the thing. There was one I missed right here that pops out a little higher on, but it's less spread out, but it's still spread across multiple factors in terms of the attributes with which it has highest mutual information. Node 3 is very selective. It achieves the highest degree of relative mutual information with only 5 of the attributes spread out across 3 or 4 of the factors. But this is the node that has the highest singular predictive accuracy against the outcome class. This is the node that came into the 4-node model as a new pattern of correlation with the attributes. It wasn't present in the 10-node model. And then finally, the 4th node also dominates in a couple of ranges, but also spreads out a rather nuanced relative mutual information dominance in a couple of other pockets of area. Okay. So imagine that instead of predicting rock versus mine here, we're trying to predict brand choice, for example, based on survey data. Well, this would be pretty cool if in the case of the social media platform that I mentioned before, we're able to go from a model that only gets about 2/3 accuracy against a 50-50 dependent variable to a model that gets 85% accuracy. Well, we can have a lot more confidence in what that model is telling us about what my clients should do, what they should try to influence and optimize in the marketplace in order to indirectly influence brand choice and app usage in their favor. Okay? But again, we have to understand why. It'd be great to have that additional accuracy, but we have to be able to understand the why behind it as defined by the particular attributes that are most driving the outcome. So there's a lot of goodness in this from a practical point of view, to the extent that it does accrue with these other kinds of data. And when I'm trying to do that kind of consulting, I typically use BayesiaLab's Target Dynamic Profile tool to do what I call intervention optimization. Okay? My client seeks to intervene in the marketplace in such a way as to influence the market outcomes in their favor. They want to know, what should we prioritize? Amongst all the product design characteristics that we could emphasize optimizing in the marketplace, amongst all the reasons to believe, all the marketing communications messages that we could use, which are the ones that we should emphasize so as to drive brand choice and product usage in our favor? So this is a prioritization exercise. We're going to intervene in the marketplace. How should we intervene? So intervention optimization is the term that I use to refer to using Target Dynamic Profile to answer that question. So I wanted to see to what extent these two different models, the BayesiaLab factors model, a PSEM kind of model, versus the neural nodes model, neural network nodes model, how might they yield similar versus different Target Dynamic Profile results? Right? So we're kind of imagining that we want more things to be minds. All right? Obviously a bit absurd, but go with me here. So we used models to compare for the Target Dynamic Profile analysis, a 10-factor PSEM. And again, it's a good comparison to a neural network because the factors directly predict the target node outcome, much as a neural network node does in a neural network. And each factor is directly connected to its defining observed measures, like a neural network is connected to observed measures through the neural network's weights. So there's an analogous structure here. And I went back to the 10 nodes model for this comparison. You don't have this kind of direct PSEM-like connection of certain nodes only to certain factors. So I used an EQ model to connect the 60 attributes through the 10 neural network nodes to the class outcome, and then ran the Target Dynamic Profile on these different nodes. So this is what the PSEM looked like. Again, you can see the mutual information with the target node is concentrated into 3 or 4 factors here and certain narrow bands of attributes. And this is the EQ model using the 10 neural network nodes. The extra nodes here are basically, these are outcome nodes that RapidMiner creates as basically it's kind of a surrogate for the actual outcome. With such high degrees of predictive accuracy, I didn't need to include these in most of the other models, but here it does, for some reason I haven't fully fathomed yet. It makes the optimization behave more predictively, if you will. So comparing Target Dynamic Profile on these two models, we do get some pretty different results. One thing we can see is that the 4 nodes model is, and what I'm showing here, the amounts of lift in predicted outcome probability that you get when you increase each one of these by 25%, as you would typically do in a Target Dynamic Profile analysis. So the cumulative amounts of lift differ, but for the 4 nodes model, you can see here the attribute that provides the most lift. It does provide lift for the factors model as well, but not as much. And the attribute that provides the most lift for the factors model doesn't even register significantly for the neural network nodes model, and so forth through the 60 attributes. So you're getting a pretty differing story here as to which of these attributes would you try to increase if you wanted more outcomes to be minds. Or back to my other example, which of these brand attributes, brand perception attributes, would I try to improve in the marketplace if I wanted to increase the probability of people choosing my brand instead of other brands? Now you get a little higher amounts of lift if you're using the factors model than you do with the neural networks model. But I think, if I'm a brand manager, I think I'd rather be going with a little less lift deriving from a 95% accurate model as opposed to a little more lift deriving from a 75% accurate model. It's a judgment call, but I think that's the way I would go. So the key points there, as I just noted, you get notably differing intervention optimization results, and even though you have a little higher lift on the factors model, you get, I think that's more than compensated for by the greater predictive accuracy that you have from the neural network nodes model. So concluding, We see that there may be good potential in neural network nodes as predictors in a BayesiaLab supervised model, and that the strong mutual information analytics capabilities seem BayesiaLab can provide a good way of explaining why a neural network model is making the predictions that it does. Further questions remain, though. Primarily, how might these results differ when we apply this to other types of data? As I said, the increase in predictive accuracy is not so great when I applied this to survey data, although it's still very significant. But we don't know until we try it with more data sets. And then the second question is, okay, this was a very simple one hidden layer network. How might this be applied effectively if you're going to neural networks with 2, 3, 4 hidden layers? And that's something that I'm sure would get much more complicated, but the concept could potentially still be applied. Okay? Thank you.